So Pascal Triangle. I've actually written the Pascal Triangle there. Right. Pretty interesting stuff. You can see a lot of use of that Pascal Triangle. So the main aim today is understand what is a Pascal Triangle and be able to construct it, and be able to identify some properties of Pascal's triangle, and be able to use simple identities associated with Pascal triangles. Now, in fact, Pascal is not the first one to discover this Pascal triangle. We call it Pascal triangle because we are definitely not used to all this. All right, it's actually some mathematician in China, 13th century, Yang Hui, actually was the first to discover this property. All right, actually, even before Yang Hui, this triangular arrangement of numbers was described by some Arabian poet and mathematician Omar Khayyam. Okay, so it is not new, but Pascal is the one who's actually making it famous, and everybody is calling it Pascal triangle. Right? I'm sure some of you might recognize the writing of this. I could recognize some, but some of that, nah, it's out. Way out. I haven't done it for so long. Alright, so Pascal triangle. Why is it so special about Pascal triangle? Look at the triangle there. Look at how it is set up. Okay. Row 0, row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, that's row. Start off with n equals to 0, n equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright? So this is row 0, row 1, row 2. Alright? And in each row, this is element 0, element 1, 2, and 3. Alright? So we always start off with 0. Now, I'm going to link this to the combinatorics notation in a few minutes. So if you look at that, for Pascal triangle, these two numbers adds up to that. This two number adds up to that. This two number adds up to that, and so on and so forth. So in fact, you could construct it pretty straightforward. I'll start off with 1, and then 1, 1, and then you know that this number will add up to 2. So it's 1, 2, 1, and this 2 number will add up to 3. So it's 1, 3, 3, these two numbers add up to 3, and 1, 3, 3, 1. So you know that outside the triangle is always 1. And constructing it is just 1, 1, 1. This is 1, 2, 1, 1, 3, 3, 1, and so on and so forth. I probably can write without thinking up to, I can write up to this row, 0, 1, 2, 3, 4, 5, 6, right? I can write up to 6 row without thinking now, because I've been using that and marking around with it for a while. So think about it, you might want to remember some of the Pascal triangles, how you write it up. Now, you can be written in an NC format. Alright, so let's think about combination. What is 0 pick 0? 1. 1 pick 0 is the same as 1 pick 1. 1, 1. 2 pick 0, 2 pick 1, 2 pick 2. Alright, 2 pick 0, 1. 2 pick 2, 2 pick 1, 2 pick 2, both of them. Yeah? So you think about choosing, you can write this in actually the combinatorial notation, the NCR notation. So Pascal rule states that each entry in Pascal's triangle is the sum of the 2 entries immediately above, like what I said. Immediately above this number, the 2 of them add together. This number, 2 of them add together. Alright, except the 1. Let's not worry about the 1. Now, knowing your combinatorial notation, which is NCR, can you prove Pascal's rule, which is NCR? This one is the sum of n minus 1. So the row number n equals to 0, n equals to 1, n equals to 2. So 3 would be the row number minus 1, r minus 1, which is this. Okay, so let me show you. This is NCR. I'm just using this as an example. N minus 1, r minus 1, this one, n minus 1, which is one row above, r minus 1, and this one here, n minus 1 CR. Can you, I'll give you 2 minutes to attempt to try to prove Pascal's rule. Right? Now, important thing to note, when you're doing all these sorts of proof, always remember n factorial is n times n minus 1 factorial. Alright? This is so useful in terms of proving. Okay. I've written my solution out. There are many ways of doing it. Everyone would probably have a different, slightly different way of doing it, but you will end up with the same result. You can start off with right hand side or you can start off with left hand side. I actually started off with left hand side. And I wrote this one out. Okay, I'm going to solve that. Gives Alright, now, how are you going to do this? It's a tricky one. You may be asked to prove this in the exam or in the test, or in a slightly different form. There are many identities that you can do, but this is the important one for you to prove, and it's going to be in your exercise as well. Alright. So when I first looked at this, it took me probably about 5-10 minutes to figure it out. So I'm going to go through it step by step with you. Now, like I said, what I've done is I split this n factorial into this. Yeah? Alright, this is the interesting one. It's pretty much like a pure maths proof. And then think about what I've done here. So, in this, I put with this n, alright? It's actually bracket n times n minus 1 factorial, correct? What I've done is, because I know there's r and a minus r here, so I've introduced minus r plus r. What have I introduced? Nothing. But I changed the log of n to minus r to n minus r plus r. Minus r plus r is 0. So nothing is there, but I've added in. I've added nothing in. Alright? That's one trick. Okay. And then the next thing is, what I've done is split it. So I use this. Assume that, let's call n minus r as a. Okay? So n minus 1 times a plus r. N minus 1 factorial times a plus r. I can take that out, can't I? It becomes a n minus 1 factorial plus r n minus 1 factorial. Correct? Where a is actually n minus r. Right? Everybody happy with that? Got the steps so far? So from there, I split that into this way. That n minus 1 factorial times n minus r plus n minus 1 factorial times r, still divided by that. Right? Now, I'm splitting it again into two fractions. Alright, it's getting clearer, isn't it? So n minus 1 factorial, n minus 1 over this, n minus 1 factorial, r over that. Okay? Now I'm going to manipulate this and this so that I can get to this bit here. Let's go to the next step. The next step, what I've done is I've manipulated the bottom, the denominator. Alright? So, using the same thing, n minus r factorial is actually n minus r times n minus r minus 1 factorial. Correct? Yeah? Agree? Very good. So, I manipulated this bit here, the denominator of the first term. Alright? And next one, what I've done is manipulating, same thing, the denominator. Alright? N minus r, instead of n minus r, I want to eliminate r. So I have changed r factorial to r times r minus 1 factorial. Yeah? It's just basically playing with this. N equals to n factorial equals n times n minus 1 factorial. Alright? Just basically playing with that. Trying to rearrange things. So, in this case, what can I do? I can eliminate n minus r. N minus r divided by n minus r is 1. I can eliminate my r. Yeah? So, from there on, I've got that. What is that telling me? N minus 1. And, there is n minus 1, both of them. Alright? Think of that term, going to the very first one. Remember the array, the notation for NCR equals to n factorial, n minus r factorial, and r factorial. Yeah? So from here, you can see that the numerator here is become that. Got it? Okay? Then this bit here. What's going to happen to this bit? Let's have a look. So here, r is because this one is minus n plus 1 minus r factorial. Okay, that would be n r factorial. Okay, if you expand this, n minus 1. Expand this, ncr equals to n minus 1 factorial, n minus 1 minus r factorial, and r factorial. Correct? Yeah? Yes, yes, no problem. And then this is the same thing. What is n minus 1? cr minus 1. Expand that, you will see that it's the same as that one. That's all. So it's basically when you're proving, you need to be able to use your knowledge, like basic knowledge of this, knowing that you can add nothing, minus and plus. Or you can multiply with something, something over something. Alright, this one, I have added nothing. Okay? It's just basically maths, it's a lot of manipulation. This is how I prove it. There are other ways of proving it. I've seen people proving it with expanding this. That's fine as well. That's not an issue. It's what you're used to. Alright? I've got my way of doing it, but there's lots of ways. Again, I must stress, problem solving. I'm not here to teach you the exact technique of doing everything, but it's teaching you how to problem solve. Alright, now, let's go have a look at example 1. I mean, you'll be able to work out example 1 pretty straightforward. because we were just going to use this, the Pascal's rule. NCR equals to n minus 1, CR minus 1, plus n minus 1, CR. Pretty straightforward. Alright. So it's just basically 136 plus 680 will give you that. Now, if you're asked to write down the sixth row of Pascals triangle, you can either start doing it 6z0 plus 6z1, sorry, not 6z, not plus, just work it out. Yeah, you can do it that way. Or, like I say, once you know the Pascal's triangle, you can just write it out straight away, up to the sixth row. It's up to you. And the thing is, if you go back to look at Pascal's triangle, it's symmetrical, correct? Once you know one half, you know the other half. And where is that? Here. Pretty much straightforward, and 63 is just 20. Alright, remember, this is 0, 1, 2, 3, 4, 5, 6. Okay? The first one is always, the position is 0. Now, example 2 is an interesting one. Prove that the second number in row n of Pascal triangle is always n for n greater than 0. So you must prove that this number, right? So we know this is 0, this is 1, this is 2, this is 3. So the second number is here, second number is here, second number is here. So this is 4. This is n equals to 4. The second number is always 4. N equals to 3, the second number is always equal to 3. So, what do you do with this? Yeah? First one, there's no second number. Is there? There's only one number. Sorry? Row 1. Sorry, this row 0. Or for 0 you don't, but that is row 1. That's number 2. One pick 1, 1 pick 0, 1 pick 1. Correct? So that's 0, let's not worry about it. For n greater than 0, 1, this is second number. 1 pick 1, 1 pick 0, 1 pick 1. 2 pick 1, 2 see 1, 2 choose 1. 2 choose 0, 2 choose 1, 2 choose 2. Alright? So how do you do it? Again, write that out. And see, this time 1. The second number is 1. Alright? So the first number is always considered 0. 0, 1, 2, 3. 0, 1, 0, 1, 2, 3, 4. Alright? So second number is same as n. Write that out. Again, what I've done here is, you know 1 factorial is 1. So from here to here, manipulated that. See, this is so powerful. N factorial equals to n times n minus 1 factorial. And therefore, NC1 is equals to n for n greater than 0. We don't have to worry about the very first one, the very top bit, which is n equals to 0. Alright, now we're going to look at some very interesting properties of a Pascal triangle. Can you do the sum of each row, please? And tell me what your observation is. Very good. So it's 2 to the power of something, correct? 2 to the power of the row number. Okay? So if you add everything up, yeah? So it's 2 to the power of 0, to the power 1, 2 to the power of 3. So look at the row number. Remember the first, the only one, that one, the top one, it's row considered as row number 0. And then you should be able to work out the sum of the numbers in 10th row and the sum of the numbers in the 12th row. So that's 2 to the power of 10 and 2 to the power of 12. That's all. Then we'll start thinking about how we're going to use these properties. In methods, you'll be using these for expanding binomial. It's slightly different focus. All right? Agree? Let's have a look at the next bit. How do we use this row total? Sorry? What? Have I done something wrong?
Just on the other slide, it was you have to take 2 to the power of 12. Right?
Which one?
Yeah, that one you just took away. It's 20. 20 in the row.
Oh, 20th, I did 12, sorry. Oh, God. My eyes when I was doing it. It's okay. My fault. I knew I'd do something silly. So now, how do we use this row total? Look at this situation. Suppose your friends say to you, I have 5 books that I no longer need. Take any that you want. Alright? If you say take any that you want, right? To me, I might look at the 5 books and say, nah, I don't want any. I might want 1, I might want 2, I might want 3, I might want 4, or I might want all 5. Alright? So how many selections are possible? In that sense, you know that you can select 0 book. You might not want all of them because it's not what I want to read. Alright? So 5 choose 0, which is 1. If you pick 1 book, 5C1 equals 5, 2 books, 5C2, 5C3, 5C4, 5C5, and it's 32. Think about how you're going to use this. How is this linked to your Pascal triangle? Row 5. Alright, so you've got 5 books that you want to pick. Now, let's say this 5 book is actually the universal set. How many subsets could there be? Including the null set. The null set is always part of a subset. So, just like this, null set, set 1 with 1 element, with 2 elements, with 3 elements, with 4 elements, with 5 elements. Right? Think about this, how you link that to using a subset. I'll summarize it for you in a few minutes. Now, let's think about the other way of doing it. This is one solution. Alright? The row total for row 5 of Pascal triangle. The other way of doing it, or for each of the book, we have 2 options. Either I want it or I don't want it. That's all. Right? There's no other option. So, using multiplicative principle or multiplication principle, we obtain the answer 2 times 2 times 2 times 2 times 2. Because either I pick that, book 1, pick that or not. Book 2, pick that or not. Book 3, I pick that or not. So it's yes, accept, no, accept or reject, accept or reject. So again, is 32. So therefore, you can see that for Pascal triangle, is really useful if you want to think about it that way. Alright? This is another solution for your information, but this is what I want to show you using Pascal information. A Pascal triangle. So just to summarize it, the sum of the entries in row n of Pascal triangles is 2 to the power of n. Alright? Now, this is the second thing I talked to you about this, the set. So you've got a universal set with size n. It has 2 to the power of n subset, including the empty set and the set itself. So, back to the book. The whole set, you've got 5 books. 5 elements in there. So, empty set, there's no element. Set with 1 element, with 2 elements, 3 elements, 4 elements, and all 5. Alright? So the second one, that's important for you to know. A set of size n has 2 to the power of n subsets, including the empty set and the set itself. So if you've got something like this, when you're looking at writing up all this, know the row numbers, and you can just work it out as 2 to the power of n. Alright? 2 to the power of row. So try the next question, please. So the question said, you take at least one book. How do you do that? Idea of complements. Use the idea of complements. One take away the whole, sorry, not one take away something. I was thinking about probability. So you use the idea of complement. You think about how many ways, how many subsets you could have. Take away the null set. The null set means I'm not taking away any book, right? Which means the rest of it is I take at least one book. Correct? Yeah? So, we write it out that way, at least one book, 2 to the power of 6, because 6 books. There's all the possible combination you can have. I might take 0, 1, 2, 3, or 4. But I know I'm taking at least one book. So here, I'm going to take away 1. Take no book, and therefore, what is left? Again, I put that down as complement. Think about using complement. Important in a lot of problem solving. Look at the problems, think about it from the other way. Can I use one, take away the other? Alright? Okay. Example 4. How many subsets of 1, 2, 3 to 10 have at least 2 elements? I'm going to stop here. I'll give you about 3 minutes to work it out. There are a lot of things you can do with Pascals triangles. I'm just giving you the tip of the iceberg, that's all. So, at least 2 elements. What do I need? Am I going to count 2, 3, 4, 5, 6, 7, 8, 9, 10? Probably not. So you know that you've got to take away the null set and the subset with 1 element, right? 2 to the 10 subsets you have for the overall, all the subsets, including the null set, subset containing 1 element. If you think about this book, it's 1 book, and subset of null set, no book, none of them. So therefore it's 1, 0, 1, 3. Again, use complement. Alright, the last one, the interesting one. Can you think about 11 squared? Pascals triangle is actually 11 squared, 11 cubed, 11 to the power of 4. But what happened? What happened at the end? So here, if you think about row 0, 11 to the power of 0, 11 to the power of 1, 11 to the power of 2, 11 to the power of 3. If you don't believe me, get your calculator, work it out. I mean, surely you know these 3, but this one, work the other 2 out. And with anything greater than 5, what happened? If you got 10 here, 10 here.
Or you add it to the...
Yeah, you add it to the...
Yeah.
The next one. So, what happened is anything above 5, 11 to the power of 5, it's 161051. Why? This 151 is directly related to that. 10, because it's 10, you move 1 up. And up there, 1. There, you've got 11. right? But 11 is another 10, so therefore, what I do is bring the 1 down, and 10, move up 5. 5 plus 1, give you 6, and you got your answer. Alright? So this is how you could use your Pascals triangle. So there are many other things that you can do with Pascals triangle. Like I said, I'm just giving you the tip of the iceberg, that's all. So the main thing from today is think about how you could prove. Use your combinatorial notation, and this is important. And I have got some exercises set up in Compass. You can start doing that now. Alright?